Okay, y'all. Been working on a power supply for a buddy of mine for, God, I don't know. I guess it's 4 years now. I'm a little slow, you could say. We finally got the pass transistor done. I guess you could say done. She's really beautiful. Um, it's a little greasy. Have to clean it up later. Um, that really came out nice. Um, but we've been thinking about things a little bit, off and on, about how to reduce the weight. And the reason why I've been working on it so damn long is because basically I couldn't get enough juice out of the transformers. Now, I figured I could overdraw the transformer by 150%. And that's usually the case with a lot of transformers. You can overdraw them to a certain percentage because of the core size. But the ones that are coming from China are sized almost 100%, so you can't overdraw them at all. Like, their spec is their spec. There's no soft um, there's no soft limit. It's a hard spec. So when they say 9.6 amps is as much as you're going to get out of that core, that's what you're going to get, because they're only magnetizing it with so much flux, and the core size can only handle so much flux. So, my mistake. I don't really care, but it's forced me to go through, I think, two rewinds, two transformer rewinds, because I don't have the cores. So I needed the primary and I needed the core. So they're not going to give you the winding that you want, because they're not set up for that right now. They're not set up to do one-offs, and that's understandable. That's kind of a big request to have them do a one-off transformer for you, um, and then ship it to you. It's that's, I don't know, it's silly. Anyway, so I got the 1500 VA transformer, which is what this is going to require. Maybe closer to 1700 VA, but it's not going to put out 1700 VA. It'll probably put out 1450 and be real close to the spec and buzz like a son of a bitch at 1500 VA, because they get really buzzy when you start saturating the core. Anyway, to get around that problem and the 16 or 24 pounds or whatever the hell it is, I think it's 24 pounds. Thing's heavy. It's big, it's heavy, and it's problematic because I'm having to center tap full wave rectify, which means I need to rewind 8 windings of 12 gauge wire on the core. And I've been thinking about that, and I really don't want to deal with that, rewinding it and then doing the tap select and using thyristors for tap selecting. And I got the logic part figured out. That wasn't too hard. And the thyristor tap select, not too bad. If you have to do it, it's not too bad. But if we can go DC, save some weight, earn back some efficiency, that was the plan in the first place. So I got me a couple of 12 volt 40 amp switchers here in their cute units, and I got me a $3 MOSFET here, and I got a mock-up little switch there. So the concern was basically, if I energize the gate, of course it'll pass the current, how hot it will get. So that's concern number one, is how hot it's going to get and constant current flowing through it. The other concern is when I open the circuit to the gate and I dump the gate charge through a 10 ohm resistor, is it still going to conduct? Because with that much current flowing through the device, any device, if you get too close to its maximum handling, or if you start getting close to its SOA, the car's going by. As the temperature increases, the SOA diminishes, and sometimes devices just don't turn off because you need to give it a negative charge to pinch the gate closed again. But we got lucky. He doesn't need a negative gate charge to pinch off, so we are good. Now, the only trouble is it's going to be running continuous, which he's getting a little bit warm. He's cool now because he's got this massive heatsink under him. But I think what I'll need to do, because this one is actually fairly cheap, it's not an $11 MOSFET, is basically parallel a couple of them up, and that will give me more handling. But as you can see, I'm going to close the switch here. As you can see, open, closed, open, closed, open, closed, open, and yeah, he's a little bit warm. But with this power supply running at 40 amps continuous day in, day out, I don't want any issues there. I want it to be very robust. I want it to be able to handle a huge load continuous. But most of the current is being dumped here from this power supply into these resistors, the gate protection resistors. So that's the only current I need on this side. And he's handling 36 amps and unlatching, which is exactly what we need for our DC tap select, beautifully. Isn't that nice? I'm not leaving it on. Leaving it on would be a real life test here. We're not quite ready for that. This is initial testing. So we'll get two of them in parallel, and we'll do real long-term testing just to make sure that it can handle the stress. And the box came in wonderful. I have both jumpers set. So you've got this jumper and this jumper set. So we've got two 1-ohm resistors, two 1 kilowatt 1-ohm resistors in parallel. So it's a half an ohm. We got a little bit of loss in the leads here, but that's entirely tolerable. We've got probably more loss across the MOSFET. We probably have a volt of loss across him. So it's a good day. Everything works. We have a third power supply, and we'll probably need a fourth to get the full range out. But I'm not sure. I don't think we can. We'll probably need. Yeah, I don't know. Have to see. Have to do some numbers. Next question is this going to handle it? And I'm not concerned. I'm not convinced this is going to handle it. It's designed to, but we have a lot of heat load, so we don't know yet. So we can build up the infrastructure here with the tap selects and everything, and make sure that it's going to do its appropriate voltage tap selects as the voltage on demand is increased. And this is real basic. So you can see exactly what it is. We've got this is the blue one's the ground lead. Okay, so it's common ground. Voltage is coming in, going through the drain, through the tab. We've got 5.6 ohm protection resistor to the gate that was in the data sheet, and we've got a 10 ohm resistor across the gate to source, and that's to deplete the gate charge, hopefully as quickly as possible. And then the source, that's the source, so it's going out to the load box into shunt. Shunt feeds this resistor, and then these are bridged. Okay, so real basic stuff here. You guys should be able to do this. Yeah, it takes a lot of machining and shit, extra support in order to pull this off, but you know, if you're eager, it's not too big a deal. It's only going to take you 4 years. Hopefully it doesn't take you 4 years. Anyway, this is good stuff. I have to get a fixture, 2 of those together, but I'm happy. It's working out. I have to get another power supply and or 2 more. Well, no, I got 3, so we need 1 more. 648. So 48 sourced, and then with losses and everything, 48 sourced with losses. It might be cutting it close. It might be 34 volts after all the losses. There's a lot of losses. Anyway, we'll cut it off there. Too much rambling.